and welcome to the Computational Fabrication Colloquium. We're very excited to have a wide range of topics that we're going to be talking about today, from HCI to networks to programming languages. So we will start with Liang. You can come up. Liang is a second-year PhD student. He's working with John. He works in HCI, specifically on fabrication techniques and tangible user interfaces.
Thank you. Thank you for the intro. All right. So today, my topic is modeling and fabricating interactivity and creativity with object properties. So I think 3D printing has been widely used these days, and we can see 3D printing has been used for rapidly making things like the mechanical components, also creating some powerful devices like the prosthetics, and also design some new fashion. But there's one problem in these 3D printed objects. They are usually very static. And in the commercial market, some companies already produce some soft printing materials like the soft PLA, NinjaFlex, or Tango. But usually people doesn't have a lot of control over these materials in the 3D printing process. And in the HCI research particularly, researchers has already explored a lot of different approaches to create deformable and interactive objects. Like this one, he's using silicon compound and some casting techniques to create some deformable parts in the 3D printed objects and make the application interactive. Or customize some printer header to print a soft teddy bear toy for your kid or for yourself. The process is really like the traditional 3D printing process, like layer-wise manufacturing, but the resulting print is very, very durable. Yeah. And also, researchers are using metamaterials, which is a kind of microstructure with many mechanical properties. In the 3D printed objects, these micrometals can be used for certain functionalities. Finally, we can, with the rigid filaments, we also can create some movable creatures using some mechanical construction. Yeah, these materials are very rigid, not soft. All right. So my big research question is how to support end users to design, model, and fabricate interactive and creative objects. And in my research approach, I focus on two parts. The first one is a computational design tool, and the second one is a custom fabricating machine. And I also investigate object properties like the material or mechanical properties and try to integrate them into these two parts. So today I'm going to show two ongoing research projects, and the first one is called Ondulate, which is about 3D printing and designing deformable objects with spring-loaded structures. I will highlight a computational design tool in this project. And the second one is called FastPrint, which is about 3D printing fluffy objects using cotton. And in that project, I created a new machine. Okay, so for the first project, my big question is how can we enable designers to rapidly design, build, and fabricate deformable 3D printable objects? And our solution is a set of novel techniques to add elastic deformation behaviors to static 3D models using a combination of spring and joints. And we are using spring because spring are widely used in mechanical engineering and haven't been investigated in HCI area. And they can exert a lot of behaviors, expressive behaviors, and also store a lot of potential energy. So first of all, I wanted to introduce the design space. We're particularly looking into two parts. The first one is spring, and based on the spring theory from the engineering, we can allow the user to control two parameters, because when we convert this object, 3D object to spring, we usually can get the size of a spring from the geometry. And also the material, we assume the material is consistent throughout the 3D printing. So the two parameters the user can control is one is the turn gap, which is the gap distance between two coils, and the wire diameter. And we also introduce the joints. We provide 5 types. For example, the prismatic joint, which is a rail and a slider. So using that joint inside the spring, the part can only compress or stretch. And also, like the other one is knuckle joint. It's basically a chain of cylindrical joint rod and socket, and you can constrain the object to deform in one direction. And we also combine individual behaviors like stretch, twist, or bending together in a compound behavior. For example, the gray area part shows 2 compound behaviors. The cylindrical joint used for twist and stretch and compress. The ball joint is used for all direction bending. Okay, I'm going to show you one quick workflow of designing a cylinder. So for example, we have this model, which is a cylinder. And the first one, we will generate a spring, which is taking over of the deformation. And the user can parameterize the parameters in the spring. And then we will generate the central constraint using a specific joint. And in this case, the cylinder can only compress or stretch. It cannot twist and bend. And finally, we generated the outer close of the cylinder, which will approximate the outer geometry of the shape. And if you see from the top view, you can see all the structure are nesting inside the model. And to enable the user to create such design, we create a plugin on Rhino. And in the plugin, the user can select part of the model and convert that part into a spring. And also the user can control the spring parameters and the joint parameters to customize the design. Okay, I'm going to show a quick video demo. So for example, you want to convert the 2 arms of the robot into flexible structure. First, we'll select the first arm and convert it to a spring. See here, it's the yellow part is the central spring, which is responsible for the deformation. The user can parameterize the spring design on the right side, the panel here. Like the user can change the stiffness of the spring and also precisely control the wire diameter and the turn gap, as I said before. And also the user can add different constraint joints. And the good thing of this design is that you can integrate a lot of different parts into one design. For example, we already finished one arm, and then we can move on to another arm and change the design. Here I'm going to show another design, which is about making the other arm only bendable in one direction. And then you will see how the user can decide the bending direction using our tool. So right now, it generates a chain of knuckle joints, and the user can change the bending angle. All right. Okay, so for this project, we create a bunch of applications. First of all, it is a snake body, so we incorporate all the design in one snake body. And the tail doesn't have any constraints, so it can be free deformed. The second one is a ring doll. We wanted to showcase the approximation of the outer close spring. The third one is a practical tool for the people with muscle weakness. So with these 2 red springs, the user can press the machine easily and cut things in their daily life. All right, so besides those applications, we also create a bunch of other applications like the jack in the box, the car with spring loaded, and also some I/O device which is connected to a digital application. The second project, our question is like, how can we enable children to rapidly design, build, and fabricate fluffy, safe, and easy to configure objects? So like when we are young, we usually play blocks and learn how to construct 3D models. And so I'm thinking maybe we can create another type of toy for them, and they can create some very safe and user-friendly objects to run the 3D modeling process. And we use cotton because cotton is very cheap and it's deformable and easy to bond, no dangerous, the material. And it has a lot of material properties, like it can diffuse the light, and also it can absorb the water, and user can use different tools to manipulate the cotton. All right, so for this project, it's at a very early stage, and we just built a machinery here. So we customized one printer, 3D printer, and we create a custom print head from the left to right. From the right to left, there's a glue extrusion mechanism which will drop the glue, which is just super glue. And in the middle, there's a mechanism called ball delivery mechanism. It will suck one cotton ball from a pack of balls and then deliver one ball, each ball one by one. And the rightmost part is the punch gun. So after, I will show you the whole process. This is a quick demo of the process. So first of all, we will drop one glue on the printed bed, and then drop the cotton ball. But it's not tightly bounded on the, then we will press it. And all the movement is controlled by the machine, and so in the future, we will generate the G code and do all the routing. Yeah, this is the idea. All right, yeah, okay. So the whole process is like we import one 3D model and we convert it to a voxelized model, and then each voxel could be represented by a cotton ball, or ideally we can change the voxels. You can combine 3 or 4 voxels as one cotton ball in the printing process. And then we will generate the G code, and based on the G code, we will do those series of operations as you've seen in the free video. And we also came up with a glue routing algorithm to tightly bound each layer of the cotton balls. And we're introducing the 1.5 layer here. So basically, between 4 cotton balls, adjacent cotton balls, we will drop another ball on the 1.5 layer. So in that way, the whole object will be very robust and tightly connected. And in the future, we want to build some applications particularly for children, like the cloud-like lamp, which will diffuse the light in a bedroom as a night light. Or we can create a soft enclosure for the robotics. And also we can add some ink, different colored ink into the cotton balls. Yeah, so I think that's a big design space for us to explore. All right, I think for this project, we also want to build a computational design tool for the children, so children can easily manipulate and design the 3D objects and in the tool, and then the system will help them generate the G code and operate the machine. And also we want to update the machine, the print head. Yeah, and thank you, and I want to appreciate my advisor, John Frolick. Yeah, I'm happy to take questions.
So maybe we can take 1 or 2 questions, or Chandra's setting up. Okay, then maybe I will ask one. You talked about developing computational design tools and also customized machines, right? What do you think is a good way to link these 2 directions?
Okay. So, because have you seen before in my 2 projects, I start this project from a specific idea. or purpose. So in that way, I probably will create a very particular design tool and a machine for the end users. And I think in the future, I probably want to create some abstraction, like in the design tool. And for example, I can extract the user requirements and design some abstraction modules in the design tool. And then also in the hardware side, on the hardware side, I also want to create some modules which can be reconfigurable for different purposes. And I think that's a better way to approach this area. Yeah.
Okay, that's great. Thank you. Yeah, I think these are really cool project and really great questions on also these, as you said, abstractions. This is something that we've been thinking a lot about, and brings us to our next talk, which is programming languages for manufacturing, and which is a great way to do these kind of abstractions. So Chandra is going to tell us about this really cool work that she just presented at ICFP.
Hi, everyone. My name is Chandra, and I'm a fourth-year graduate student in the Programming Languages and Software Engineering Lab. And today I'm going to talk about functional programming for computer-aided design. So as we already saw from Liang He's talk, CAD and 3D printing is becoming almost like a revolution now. And there are so many different applications for 3D printing these days. So starting from automobiles to space programs to medicine, such as customizing prosthesis, the applications are just numerous. And what's even more exciting is that recently, due to democratized fabrication, the price for 3D printers and other similar devices have gone down. And as a result of that, if you have a couple $100s to spare, you can actually quite easily buy a 3D printer and start printing various types of things for day-to-day life, various tool parts, or just devices for aesthetic purposes. And this is all actually really great. And as you can see, we have printed a lot of things in the past couple years in our lab itself. So what's a problem in this space is that the software pipeline that is currently used in fabrication has certain challenges. And the particular challenges that I'm going to talk about today is about design tools. So the first thing you do when you 3D print something is you design a model. And for that, you use various types of CAD packages. And it turns out that these CAD packages are actually really hard to use, especially if you're a hobbyist and you've never done this before. The learning curve is really steep. A lot of these are actually also very expensive, and often there isn't really any proper specification. So you kind of try out something and it doesn't work, then you do something else, and eventually you get it to work. So to avoid all of these problems, what people do today is they just go to these repositories like Thingiverse and GrabCAD, and they just download models from these repositories. And now this is actually really great because once you download something, all you have to do is slice it and print it. So you don't need to buy any CAD package. You don't need to understand how to design models and so on. So this is great as well. Unfortunately, when you download a model from these websites, most of the time these are in the form of a mesh. And these meshes are really hard to modify. So let me tell you a little story that can demonstrate this better. So a while ago, I downloaded this model from the internet. So this is a hex wrench holder. So if you go to IKEA and you buy a set of hex wrenches, then you can put them in this holder and just to store them. So I put my wrenches in, and I was not very happy because my wrenches were not sitting parallel to one another. And it was really important for me that they were parallel. So I went and got a mesh editing tool, and I started to modify the mesh. And it turned out that just the simple modification, which was just rotating a hole a little bit, was actually really tedious. I was constantly breaking the mesh, and in the end I just gave up. And I was just sitting there and wishing that I wish I had a higher level program that was a little bit more abstract, so that I could look at it and understand what's going on and maybe make this change much easily. So what do we actually want here? We want some tool that can take any mesh and convert it to a CAD program that is equivalent to that mesh. So that is exactly what I'm going to talk about today. So we have built this tool called Reincarnate that takes a mesh and gives you back a CAD program. And if you compile that CAD program, you're going to get back that same mesh. So if you give this mesh that I showed you before to our tool, what it's going to do is it's going to produce a program in a language that we built, and it looks like that. And once you have that program, in this case, the modification was literally one line, right? So we added a line, and that line was rotation about z-axis. And once we did that, we printed it again, and I was really happy because everything was parallel, and it was great. Okay, so now that we have seen that this is a useful tool, let's try and understand how we build this. So in order to build this tool, we had this key insight that the fabrication pipeline can be viewed as a compiler. Okay, so why is that the case? Well, because everything we do in this fabrication world is actually write programs in certain languages, compile them to certain different types of representations, and ultimately we generate G-code, which you can think of as assembly for 3D printers. And that is what the 3D printer actually interprets, and it moves the extruder and prints your thing for you. So this can be viewed as a compiler. So if it is a compiler, then what are the languages that are the sources and the targets? So the language that we care about is the topmost language, which is the CAD language, right? So here is an example of a language that we built. If you're familiar with languages such as OpenSCAD, then this might look similar, So this language can support various primitives such as cubes and polyhedrons. It can support various affine transformations such as rotation and scaling and translation. And it can also do various binary operations such as union, difference, and intersection. Okay, so this is our source language. So we are going to write programs in this language, and it will be compiled down to a mesh. So mesh is a data structure, which is a list of faces that represent the surface of your model, right? So it's not a solid representation, it's a surface representation. And you can think of a mesh as an intermediate representation, which is actually really great if you want to do any kind of geometric computations. And it turns out that these are the formats that are most popularly used in online repositories like Thingiverse and so on. So these are really useful. So now we have seen a CAD language and we have seen a mesh. And I told you that we can view this fabrication pipeline as a compiler. So let's just write the compiler. So the compiler is a function, in this case, that takes a CAD program and gives you back a mesh. Okay, so let's see what it does for a cube. So it's going to produce the mesh for a cube, and if you render it, you can see that it's a cube, right? So it's a cube. The bottommost left corner is at the origin, and the dimensions are all 1. Okay, so now what happens if you want to do something more complex? So for example, if you have an affine transformed CAD, so it's very similar to what you can expect from any other language. So it's going to recursively compile the child and apply the affine transformation to the vertices of that child. And similarly, if you have a union or a difference intersection, you're going to compile the children and then apply the operation to the meshes of the children. So let's actually run this compiler on this simple example and see what happens. And we will actually run this using small steps. So at every step, we are going to focus on a part and compile it down and then move on from there. So here's a program in the language that I described. So this is a union of a cube and another cube that is translated by amount 2 about the x-axis, along the x-axis. So what the compiler is going to do is it will focus on the first child, so which is a cube, and it will crunch it down to a mesh. And we already saw how that happens. Now after that, it is going to focus on the next child, which is the right child, and then it will crunch that down to a mesh that corresponds to it. Now once it has compiled everything down to the meshes, finally it will apply this union to the meshes, and that will give us the final mesh for this model. Okay? But this is actually not what we wanted, right? We want the backward process. So what the solution that we actually care about for not having to learn any CAD and just magically download models and decompile them to CAD programs is actually to go in the backward direction. So starting from a mesh, we want to go back to a CAD program. And the way we are going to do that is by using a technique called synthesis. And essentially, in this case, what that boils down to is just flipping the arrows of the compiler. Now, you might be wondering, how is that happening? Well, because we have already done all the hard work, right? We have built a compiler, and we have used these small steps to make the compiler make progress. And because we have done all of that, now we can magically get a synthesis tool by just flipping the arrows of the compiler. Now, of course, nothing comes for free. There are still some challenges that we need to address. And in particular, there are 3 things. So the first thing is, when you go in the forward direction, you lose a lot of information, right? So when you want to go backwards, you need to find a way to get that information back. If you look at that blue lozenge on the slide, the kind of information that we are losing here is just by looking at that shape, you can't actually tell how it was actually designed, right? In this case, it was designed by intersecting two cylinders. But it might have been a primitive in the language, right? So we don't actually know what how it was manufactured, or how it was designed. So how do we get back this information? So it turns out that there is a technique called evaluation context. I'm not going to talk about the details of this, but it's a technique in programming languages that can actually let you use the geometric context to replace certain parts of the mesh by some primitives that are provided in the language. So we can use that to retrieve the information that was lost in the forward process. The second problem is that there are a lot of geometric challenges that we need to solve in order to go backwards. So how do we do that? So we implemented various oracles that can guide the synthesis process. It turns out that there are so many different CAD programs that when you compile gives you the same mesh back. So we need to be able to make this entire process much more tractable than it actually is. And these geometric oracles help us do this. And the third problem is that the entire backward process is actually quite non-deterministic, right? Because at every step, there are so many different directions in which you can go, and you don't want to go in all those directions. You need to be able to follow certain directions that can lead you to a proper CAD program that is actually what you want. Okay, so the way we do that is by using search. So we have actually built this tool. So we have built a compiler, and we have also built this decompiler, and we have used it on about 20 to 25 models that we downloaded from Thingiverse. And so Thingiverse happens to be one of the most popular repositories for sharing designs for 3D printing. And we were able to synthesize CAD programs up to 200 lines of code. So basically, that brings me to the end of this talk. So the takeaways from my talk are that functional programming is great, and you can use it in this really exciting domain of fabrication. And in particular, the things that you can do with it is you can design domain-specific languages, you can provide semantics to them, you can build compilers, and you can even prove correctness for your compilers. And after doing all of those exciting things, you can even do more cool things, like build fancy decompilers and program synthesis tools that can let you go back from meshes to CAD programs. And with that, I would like to thank my collaborators in the project. And if you are interested, I would recommend you to go and look at our tool. And if you have any questions, I'm happy to take them. Thank you.
So questions? You can start setting.
This is really cool. How did you come up with the set of shapes that were going to be in your geometric oracles?
The shapes in the language, or you mean in the oracles?
I don't know which I mean.
Oh, so okay. So right now, the language supports shapes that are very like cube-like. So you can have like prisms and cubes and cuboids. And for more fancy things like spheres, we have like hard-coded models for like primitives for them. But it would be cool, and we would like to extend it to support like real curves and so on. So all the oracles that we have are actually using those primitives that I just mentioned. So cubes and cuboids and prisms.
Next up is Vikram, who is a PhD student in Networks and Mobile Systems Lab. And he's going to be telling us about his work that he just presented at WIS on wireless analytics for 3D printed objects.
All right. Hi, everyone. So today I'm going to be talking about wireless analytics for 3D printed objects. And this is joint work with Justin in our group, as well as another undergrad, Ian, and advised by Jen and Sham. And so before I go any further, what do we mean by analytics, wireless analytics? Our goal in this project is to track the use of functional 3D printed objects over time. So for example, if we have things like this Phoenix hand, it's a prosthetic hand, these types of things have a pretty high rate of abandonment. But what if we could track when a user is actually opening and closing this hand, or even how much they open and close it? Tracking these kinds of things could give us important information about their use to address these issues of abandonment. And we could also think of other, everyday objects like this plastic pill bottle here. If we could track things like when a user actually unscrews the cap, we could make sure that someone has either taken their medication or, say, make sure they haven't taken too much. So really, our goal overall is to embed wireless sensing into these 3D printed objects. We can also think beyond everyday objects, like to things like this robotic arm here. If we could use a printed object or track the motion of a printed object and map that to this robot arm, there are all kinds of other cool things that we could do. Now, at this point, I've shown you some applications of what we could do if we could track the use of printed objects. But, and the most obvious way to do that would be to embed electronic sensors in them. The problem is that this requires first designers to have a pretty strong understanding of the electronics and circuits, on top of being experts in mechanical design as well. And second, any electronic component requires some kind of power source. So that means then you'd have to deal with batteries or have an RFID reader pretty close by. So in this work, we take a different approach. And instead, we co-design our 3D printed objects and sensors to create completely plastic objects that can communicate without any electronics. We call this work Printed Analytics, which is a wireless and circuitless platform that can capture, store, and transmit information about the use of 3D printed objects. And I'm going to explain how this works in the context of a couple of motivating applications. First, printed prosthetics, then smart pill bottles, and a wireless insulin pen. So to give you an overview, I'm going to start by explaining how we can 3D print objects that can communicate wirelessly. Then I'll go on to talk about how we can decode the wireless signals and how we can use that to track motion. And last, I'll talk about how we can actually store information in these objects to enable analytics outside of our wireless range. So first, I'm going to talk about how we actually print these objects. And to really understand this, first we need to answer the question, how can a plastic object communicate? The answer is that unlike things like our Wi-Fi chips that exist in our phones and everything else, our printed objects communicate using reflections. And this requires three different components. The first is an antenna, second a switch, and then the message that we want to transmit. The way this works is we have an incoming radio signal that hits this antenna, and then when we toggle our switch on and off, that changes how that antenna absorbs or reflects a signal. And so by controlling that switch, we can produce a changing reflection over time and use that to communicate information. So next I'm going to go into a little bit more detail and walk you through how we build each of these components. So first off, how do we 3D print an antenna? The first step in our design process is to start with a well-known reference design for an antenna. But the problem is that we can't just copy a design for a metal antenna because the performance of an antenna depends a lot on things like the material properties. And in our case, we're going to be using a conductive 3D printed filament to actually fabricate them. So our next step is to take this original design and then model it in an electromagnetic simulator to optimize parameters like the length and the width to get the frequency and bandwidth that we want. And then last, we actually fabricate this using, like I said, a conductive 3D printer filament on a dual material printer, and we get something like this antenna you see here. That's something that we actually use in our printed objects. So next, how do we build a switch? Now, remember that for things like a pill bottle, like I'm showing in this video, that switch has to be able to move in two directions. So the main components of our switch are we have a spring and a conductive contact. So on the left here, we have our cantilever spring, which can actually move both up or down because of its symmetric design. And what happens is we have this gear, whereas it turns, basically as it's turning clockwise, it's going to push that spring in one direction. When it turns counterclockwise, it'll push it in the other. On the reverse side, we have our antennas and the switch contacts. So again, as that gear is turning, it's going to push those contacts to either touch the antenna at the top or touch the antenna at the bottom. And that's going to create the changing reflection. So here's an example of our switch in action integrated into the Phoenix hand that I showed you before. And we can see that the switch is either moving up or down to touch the antenna at the top or the bottom. And this creates this pattern of changing reflections that we see at the bottom. That's what we get at our receiver. So next, now that I've shown you how we actually print these things, let's go on to understand how we can decode these signals that we get from them. So the first step is we record the raw signal on a software-defined radio. And the problem is we can see in this raw signal those little peaks that I showed you before, but we also have lots of noise from the environment. So the next step is we go through and we apply some filters and count the number of peaks that we have in this signal, which corresponds to our data. In the interest of time, I'm going to skip through some of the details about how we extend the range of our transmitter. But to give you an overview, our system works up to about 4 meters from our access point. So next, if we look at how we can actually track rotational motion once we've decoded our signals, here's another video showing the Phoenix hand again. And what we see here is as we turn that gear, we get 6 peaks this time. And what we can do is we can map that number of peaks to the number of times, or basically the amount that gear is turned and the number of times it's pressed the switch. And we can see that across a whole range of 180 degrees of motion, we can figure out how much this thing has moved. The other question is, of course, how do we figure out the direction that the gear is turning? It could be going counterclockwise or clockwise. And the way that we do this is by using this asymmetric gear design, where we have this pattern of 6 teeth followed by 4 followed by 3. And if we look at this pattern of peaks that we get on our receiver, by simply looking at that sequence and the order that it appears in, we can figure out whether our gear is turning clockwise or counterclockwise. So last, I'd like to talk a little bit about how we can enable analytics outside our wireless range. And I'm going to motivate this by talking about an application like an insulin pen. Now, what we want to do here is we want to store the number of times this has been pressed, and we want to accumulate the number of button presses to know how much insulin has been dispensed. And last, of course, once we have that data stored, we want to upload it once we're back in our wireless range. The key idea here is that we're going to store information in the rotation of a spring. So the way this works is when you apply force to press down the button on the insulin pen, it's going to coil up this spring. The question, of course, is how do we do that in a controlled way? And we do that by using a ratchet mechanism to coil up this spring in a controlled fashion. So the way this works is a ratchet is a mechanism that can only turn freely in one direction. So if you look at the pattern of teeth that we have here in these grooves, when the ratchet turns in one direction, it can move freely, but in the other, it's going to come back and get stuck. So what we can do with this ratchet is when it's turning in one direction, we accumulate all of our rotation and store up energy in that spring. And then when we press a button, we'll release that and we get our data back. And here's a brief video showing how that works. Again, we're pressing it down, coiling up the ratchet. And in just a second, I'm going to press a button to release that. And we get our backscattered data. So some quick thoughts on how we can improve on this in the future. We're currently working on reducing the form factor of this to make it fit into smaller objects, storing additional information about printed objects, and hopefully increasing the wireless range from across a room to, say, across a whole home. So to conclude, I've shown you how printed objects can communicate and how we can store information about them, and how we can enable analytics for applications like printed prosthetics, pill bottles, and a wireless insulin pen. Thank you.
When you're doing the analysis on the antenna design, was that like Consol or something, or?
Yeah, it was actually HFSS.
Okay.
Yeah.
Yeah. So there, can you take into account the structure of 3D printed conductive material?
Yeah, so that's actually a great question. That's not something I found a way to model very well as far as like the different layers that we have and how those will impact the structure of the printed object. But I've definitely seen that, you know, the what you get when you actually model it in standard electromagnetic simulators isn't quite the performance that you get on the actual printed object.
Yeah, great research problem.
Yeah, definitely. Anything else? Yeah.
Yeah, so it seems like, in particular with some of the applications that you talked about, you can imagine really serious security and privacy concerns with the data that you're collecting. So if you have the transmitter and the receiver, are there strong guarantees that like only the receiver can actually receive that data?
Yeah, so one thing right now is, of course, our wireless range is limited. The other thing that we've been looking at is how we can encode or like basically have some kind of encoding on the gear to encrypt like what information we're sending. So then you'd have to know that information to be able to decode the signal.
And next is Megan. She is co-advised by Jen and Scott Hudson at CMU. She's spending the year with us here at UW, and she's going to tell us about some cool work on knitting.
This is research done in collaboration with the Carnegie Mellon University Textiles Lab, along with my collaborators Leah Alba, Tisha Sethapakati, Jessica Hodgins, Jennifer Menkoff, and Jim McCann. And I want to start off by saying this is not a project about 3D printing, and we did not invent a knitting machine. In fact, almost everyone in this room is probably wearing something that was made with an industrial knitting machine. If you're wearing a sweater because it's cold outside, industrial knitting machine. If you're wearing socks, industrial knitting machine. If you're wearing an orthopedic brace, industrial knitting machine. If I actually don't think this furniture is knitted, but most furniture that has any stretch to it, knitting. And there's lots of other interesting applications of industrial knitting in the future. You can create 3D shapes with knitting, which means that if you dip those 3D shapes into cement, you can make really lightweight bridges or other architectural structures. And at the CMU Textiles Lab, we're really interested in thinking about how can we make industrial knitting machines more accessible from a computer-aided design perspective. So the first place we started with this in 2016, when we were the Disney Research Pittsburgh Textiles Lab, was to build a compiler for the low-level machine instructions that run these machines so that we can create different knitted primitives relatively easy, like this teddy bear outfit. And then this year at SIGGRAPH, we started to think a little bit more about complex shapes. And so we can do something like take a 3D mesh of, say, your favorite Stanford bunny and generate a 3D or a knitting instructions. But the next step we're starting to look at is thinking about texture. So this is my co-author Leah Alba's work. She presented this work at a fashion show. And she was thinking about different ways of controlling textures and the interesting properties of textures. So you can make a really ruffly skirt, or you can make this interesting shoulder pad structure. But the problem is that creating 3D knitted structures is really difficult. So what we started with is a very simple pipeline that starts with a parser of a hand knitting language. We did not invent this language. It actually exists. It wasn't designed for computers. It was designed for people. And we compile this down to something that we call a knit graph, which is just a basic representation of the functional properties of a knitted structure. And we can apply a lot of interesting algorithms, pretty standard classic graph algorithms, to manipulate these structures in interesting ways and combine them together. And then we throw this into knit out, which is the term for most of the prior work I was showing earlier, and we get knitted results. And we have, based off of our sample from a online repository of knitting, samples, we have 400 plus swatches of knitted textures. So if anyone wants to see one of these things live, come down after the talk. But for the brevity and shortness on time, I'm going to stick to just these kind of first three components. And I'm going to start with the KnitSpeak parser. So the state of the art for industrial knitting is this terrible, terrible image editing tool. So if you want to think about knitting as a bunch of stitches kind of all structured in rows and columns like a picture, you might start to think, well, let's just name every stitch a color. And let's have someone label every single pixel as the stitch they want at that space. But if you're repeating a structure over a large series of space, maybe 10,000 stitches, 1,000,000 stitches, that's about the number that would go into a sweater, this can be really tedious. And so fashion designers don't do this, engineers at knitting machine companies do this. But there are lots of people who know about knitting, and they are not engineers. And in fact, they have invented their own ways of describing knitted structures so that they can render these things on their own. And their instructions look oddly like a programming language. So they give you different commands for all of the instructions in a specific set. They may repeat these commands over time and say, like, do this particular row on row 1, 3, and 5. And then they have charting tools that can help them represent these visually so that they know what they're making as they're knitting it. And so we did a really simple thing. We just took this language, we built a parser for it. It rendered pretty accurately across the sample that we looked at. And now we can generate these swatches of different interesting knitted textures. And this reveals some interesting things about knitted textures. They have lots of fun properties. They can stretch and scrunch in. They can have opacity change where they look like a lace where you have lots of holes through it. And they can even change the shape entirely of a rectangular fabric and make it tilt onto its side. So how do we represent, what are we outputting from this KnitSpeak parser? Well, to explain that, I'm going to have to explain how knitting works, and specifically this idea of a loop-de-loop constraint. So if anyone's ever held a string and wrapped it into a loop, you know that if you pull on two ends of that string, the loop's going to fall apart, right? But if you pull a loop through that loop, the loop that you originally made, the green loop at the bottom, is going to be stable. And you can pull it through in either direction, and now you have two different sides of a knitted structure. So if you're wearing anything knitted, I encourage you to flip it over and notice that it looks completely different on the opposite side. This is the notion of the two simplest stitches you can make, a knit and a purl. But we can combine loops, so we can decrease the number of loops in a row by pulling them through on one stitch. Or we can increase the number of loops by adding what we call a yarn over, which is just a loop with no parents. And then we can do even weirder things, like we can start to cross these loops over one another, and this ends up making a stiffer structure, and it also kind of embosses the fabric so that it looks like there's a stitch that's traveling at a diagonal. And if we make a basic grid of these different loops that are stabilized by one another, we have a knitted structure. And a knitted structure is a linked list of loops called a yarn. Or it's a series of loops that are connected to one another in what we call a knit graph. So a knit graph is where each node is a loop, and the directed graph between them is how the loop is pulled through another loop with this loop-to-loop constraint that all loops must have a child or else they will unravel. So let's think about a particular problem with these knitted structures. These textures are great, except that they're output in tiles that usually have a resolution of somewhere between 1 centimeter and 1/2 foot. So that's really poor resolution, but because of this loop-to-loop constraint, there's lots of dependencies across these tiles. And so if we want to remove any of these stitches, we have to do so carefully. So in this case, in this texture, which is about 4 inches on either side, you have 4 tiles. You have a resolution of 1 inch. But removing things from images, or something that looks like an image, as nothing new. Back in 2007, Avedon and Shamir invented seam carving, which is just a dynamic programming technique for removing a seam, not to be confused with these seams in this paper, of pixels that are the least relevant in an image. And so we want to apply the same approach to these tiles of texture. And when we think about the value of a single stitch, we're going to think about first the functional constraints. How many loops depend on this particular loop? That's a bug. Oh well, we'll skip forward to the algorithm. So what we're going to do is we're going to assign these values, and you might already start to see a path of 1, 1, 1 in red, and think that kind of looks like the chevron that was represented by this texture. And then as we sum up the value of all of the smallest dependencies, we get this path that follows those black dots. And we can remove those black dots from the image, or the knitted structure, and now we have a slightly reduced texture, which means that we can make smaller and smaller tiles, and our resolution is back down to a stitch. And what I want you to take away from this idea is that machine knitting is a unique fabrication tool that has been relatively unexplored in the literature. It can produce complex shapes with fabric without sewing. And then knitted textures are more interesting because they have these functional and aesthetic properties. They're stiff, we can control the drape, they stretch in different interesting angles and ways. And finally, we can express them as a simple node-link graph, which means we can apply all of these classic computer science algorithms to manipulate them in interesting ways. Are there any questions?
Did you ever have any problems where things in NitSpeak didn't map well to the machine knitter?
So we actually got lucky that there is, so the charting tool that I'll go back to that one. That image, the chart image comes from, is generated by a place called Stitchmaps, which has a language already in it. So we knew that everything would be parsable. It does end up lining up that they engineered their language particularly well, that if you look at the majority of published books of knitted textures, they use a very similar form to this. It's essentially following the same grammar, so that we could have a sample from books that are out there as well as this entire repository where we were guaranteed that they would parse, because they wouldn't have been a chart on the website if they didn't. We had a few exclusions where there are properties in their language that actually can't be expressed on a knitting machine because hand knitters have more control. If you want to see samples of things that can't be machine knitted but can be hand knitted, I've got a sweater with a blackberry stitch that's particularly difficult for the machine.
Is there a version of NitSpeak for circular knitting machines as well?
Yes, and the only change is that instead of saying row, 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 you say round, 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 round. It's the exact same language, and the graph can be represented both ways because we represent the order in which the loops occur as a linked list, and so we just say, like, as you move to the next row, the linked list doesn't have to shift backwards.
Yes, so this was a super cool talk, thanks. But one quick question about making or incorporating like different materials into this framework. So to what extent does it take into account the differences in, say, swatches that are produced by running the same set of instructions over like a different sort of like fiber?
So we have only knitted these in cashmere, which is a relatively expensive activity, but you can knit on an industrial knitting machine with a variety of fibers. Shimasheki, who is the company that produces our knitting machine, sells a lot of fibers, including conductive fibers, meaning you could probably make circuits. We haven't explored it yet, and we know that it will affect properties like the stretchiness and the gauge, because those are as correlated to the material as they are to the overall structure. One of the things we're looking at in future work is that if you take these different properties, is there at least consistency in how they change so that you can model things in regular yarn, but then predict them for something like a metal.
So let's thank again all the speakers, and there will be a front if you guys have any questions.